Hello, my name is Maria Molina, and today I am going to be speaking to you about extremes in a changing climate and their societal impacts. We will discuss some of the physical basis regarding changing extremes, why it can be very challenging to characterize certain changes in extremes, and what some of the latest research says about these changes. But first, who am I? I am currently an assistant professor in the Department of Atmospheric and Oceanic Science at the University of Maryland in College Park, which is in the United States near Washington, D.C. My research focuses on climate and extremes data science, where we ask questions like, how are extremes started? And can we improve the identification of their precursors? And I am also affiliated with the University of Maryland Institute for Advanced Computer Studies, where I collaborate with machine learning scientists on societally relevant problems. However, I previously had a very different career. For about 6 years, I worked as a broadcast meteorologist in New York City, during which time I had the opportunity to cover weather events across the country. A career as a broadcast meteorologist entails much more engagement with the public on a daily basis than work as an assistant professor or a researcher, including communicating how to prepare for and what to do after extreme events. During the approximately 6 years that I worked as a broadcast meteorologist, I covered a number of extreme events, some of which set new records and produced impacts that were previously unimaginable. However, the severity of these events cannot necessarily be solely attributable to global warming. The severity of some of these events could also be associated with the natural climate variability of the Earth system. As a broadcaster, I regularly engaged with the public and built trust over the years. It was critical that I discuss and contextualize these extreme events for the public. This communication included forecasting of extremes before they happened and detailing recommended practices for preparations and/or possible evacuations. However, after extremes, there can be other questions that arise that require a deeper understanding of extremes in the context of climate change. For example, following extremes, the public often wants to know how an extreme compares to past events in the historical record, and whether we will see more extremes in the future. Therefore, whether you are a climate scientist, a television meteorologist, or a local forecaster, it's likely that questions about climate change and extremes will arise, and being prepared with the data analysis skills is a key step. Before jumping into more specific analysis methodology and details regarding extremes in a changing climate, it is important to understand some of the physical basis behind these statistics of extremes, and we do just that in the next few slides. The Earth system is very complex, as illustrated in this figure from the IPCC Fourth Assessment Report, which shows the main drivers of climate change, or in other words, the main factors that influence the radiative balance between incoming solar shortwave radiation and outgoing long-wave radiation. While there can be natural fluctuations in the amount of incoming radiation, human activity influences emissions of greenhouse gases and aerosols, which are involved in chemical reactions in the atmosphere. The concentrations of these particles are involved in a number of feedback processes influencing the amount of outgoing long-wave radiation that is ultimately emitted back to space. We can also look at the Earth system beyond the main drivers of climate change. The Earth system has various components, such as the land, the atmosphere, and the ocean, that are coupled via fluxes and physical processes. Interactions between these components are shown with two-way arrows in this figure from the Fourth Assessment Report of the IPCC. In addition to increased temperatures related to increases in greenhouse gases and changes in aerosol concentrations, changes in evaporation and precipitation are another area of study in climate science that can have significant societal impacts and downstream effects to other parts of the Earth system. Air temperature and water vapor have a relationship that is described using the Clausius-Clapeyron relationship, as shown in this figure. It is well understood that as air temperature increases, vapor pressure also increases. More specifically, the Clausius-Clapeyron rate states that for every degree Celsius increase in air temperature, the capacity for the atmosphere to hold water increases by approximately 7%. The rate of increase can vary depending on other factors, such as whether the air mass is over water or land. This relationship has implications for water vapor around the world. However, we need to be careful when interpreting the Clausius-Clapeyron relationship. A short article was recently published in the Proceedings of the National Academy of Sciences discussing misinterpretations of the relationship and clarifying that while the Clausius-Clapeyron relationship describes how temperature and water vapor are related, it does not explicitly control for precipitation. To be more clear, that means that there are other factors that influence precipitation beyond air temperature, such as the atmospheric circulation, including the position of the jet stream and disturbances that travel along it, and mechanisms providing low-level convergence that can enhance lift for subsequent precipitation. The nature of precipitation itself, such as whether it is convective versus stratiform, and associated microphysics, also play an important role in precipitation. The Clausius-Clapeyron relationship also assumes that there is moisture available. Lack of moisture, which may be possible at high temperatures in certain climatic zones, can be a limited factor in the scaling. Therefore, surface temperature alone is not necessarily a good proxy for atmospheric moisture in all cases. Challenges with interpreting changes to extremes does not only arise from physically based relationships or processes, though. There are also human factors that can leak into our data sets, creating artificial trends that we may misinterpret as changes to the climate system if we are not careful. We highlight a few examples of these challenges in the next few slides. One type of extreme that exhibits numerous issues with long-term trends includes severe thunderstorm hazards, which encompass large hail, damaging winds, and tornadoes. In the United States, tornadoes are rated using the Enhanced Fujita scale, which estimates the strength of a tornado by assessing several damage indicators, or, in other words, how much damage the tornado caused. Over the years, however, there have been changes in tornado ratings. The Enhanced Fujita scale replaced the Fujita scale in 2007, which created discontinuities in the rating and characterization of tornadoes. In fact, if you were to assess tornado path width without accounting for this change, you could naively assume that tornadoes have become wider in recent years, as shown in this figure. Another potential issue related to severe thunderstorm hazards involves hail. As this figure shows, most hail reports are received along major roads where there are more people traveling that may encounter hail from thunderstorms and thus report them. Wide open fields or vegetated areas that don't have roads seemingly do not receive hail, which we know is not accurate. So how could we correct or account for some of these issues in our data sets of extremes? Well, one way is to consider an environmental perspective instead of solely relying on observational data sets that may be plagued with artificial trends and biases. For example, in the case of severe storms, we know that certain environments, such as convective available potential energy and wind shear, create more favorable conditions for severe hazards to be produced by convection. In the study cited here, we considered climate variability of the significant tornado parameter, which considers numerous environmental variables that have been associated with intense tornadoes in the past. In addition to assessing trends in observational products or environmental data produced using numerical models, there is also research that is conducted that falls under attribution studies, where we can estimate how changes in the background climate related to global warming may have changed the likelihood and/or intensity of an extreme event. We will provide examples for some attribution studies that have been conducted related to tropical cyclones, but first we provide a brief physical background on tropical cyclones. A tropical cyclone is a warm core, low pressure system with an organized circulation. There are several favorable environmental conditions that can help a disturbance develop into a tropical cyclone. This includes ocean temperatures warmer than about 26 degrees Celsius, sufficient moisture near the mid-levels of the troposphere, some vertical instability, a pre-existing near-surface disturbance, little vertical wind shear, and some minimum distance from the equator, such as more than 400 kilometers, for the Coriolis effect to aid in the maintenance of low pressure. Despite our detailed understanding of the environmental conditions that are favorable for tropical cyclone development, we still don't fully understand why some disturbances become tropical cyclones, but others don't at the storm scale. Numerous theories surrounding tropical cyclogenesis exist and are debated. Here we provide an excerpt from one study that demonstrates the important contribution that cloud feedbacks play in tropical cyclone development and intensification related to localized atmospheric warming within the storm. Uncertainty related to tropical cyclogenesis, along with climate model limitations related to imperfect physical parameterizations and coarse resolutions, ends up propagating into climate scale analyses where we want to understand how the frequency of tropical cyclones may change in a warmer world. This image from a recent study published in the Bulletin of the American Meteorological Society illustrates this point. The projected change in tropical cyclone frequency is both positive and negative across most basins in the world. However, there are other impacts from tropical cyclones that we have greater confidence in, such as the projected increases in rain rate, also shown in this figure. Focusing on an impacts perspective can help better characterize extremes in a changing climate and delineate the processes that we have high confidence are changing from those with lower confidence. For example, from the IPCC 6 assessment report, we have this abbreviated list of impacts related to tropical cyclones with comparatively higher likelihoods as compared to our confidence in projected changes in tropical cyclone frequency. We can more clearly communicate that total precipitation and precipitation rates associated with tropical cyclones are likely to increase in the future. Sea level rise will increase vulnerability to storm surge related to tropical cyclones, and intense tropical cyclone proportions are also likely to increase. Tropical Cyclone Harvey, which occurred in 2017, is an example of a storm with extreme total precipitation. The tropical cyclone made landfall in southeast Texas and moved very slowly over the region, with rainfall totals exceeding 100 centimeters. The Houston metropolitan area saw catastrophic flooding. Following the event, a modeling study was conducted to assess how different Clausius-Clapeyron scalings could have impacted water vapor content within the storm. The hypothesis underlying higher Clausius-Clapeyron scaling is related to extra heat of condensation that can provide additional energy to drive the circulation in a well-organized system. Following the creation of these simulations and extrapolating results to Tropical Cyclone Harvey, the authors concluded that global warming made the precipitation associated with Harvey about 15% more intense. Tropical Cyclone Sandy is another storm that is heavily discussed in the context of the potential influence that climate change had on its extensive damage in the northeastern United States, particularly in relation to storm surge. Sandy's origins, however, were in the Caribbean Sea, south of Jamaica. After landfall in Jamaica and Cuba, the storm moved north over anomalously warm surface waters, eventually undergoing a transition from tropical to no longer tropical, and then made landfall in New Jersey in the US, leaving behind significant destruction. Zooming farther into the Northeast, the damage in New York City resulting from Sandy storm surge was immense. For example, the East River along the eastern edge of Manhattan overflowed its banks, which flooded large sections of lower Manhattan and numerous subway tunnels. Damages along the east coast of the United States have been estimated to be over $60 billion. While the potential influence of climate change on the storm has been a topic of intense debate, contributions to damages from sea level rise driven by anthropogenic climate change are more clear. To quantify the effect of sea level rise on damages, a recent study published in Nature Communications simulated water levels and damages both as they occurred in the actual climate and as they would have occurred across a range of lower sea levels corresponding to different estimates of attributable sea level rise. They found that approximately $8.1 billion of Sandy's damages are attributable to climate-mediated anthropogenic sea level rise, demonstrating that climate change made this specific extreme event more expensive. While climate change is related to many different components of the Earth system, the societal impacts related to extremes, which can be destructive and devastating, are a large reason why this is such a significant focus in discussions about climate change. Now we will take some time to discuss the societal impacts related to extremes in a changing climate. Numerous research studies in recent years have demonstrated that certain groups of the global population are more susceptible and vulnerable to extremes. These groups include underserved communities, historically marginalized people, and lower socioeconomic groups. Before extremes, these groups may be limited in their ability to prepare or evacuate, and afterwards may be limited in their ability to rebuild or relocate. Thus, these communities experience a disproportionate vulnerability to extreme events in a changing climate. A case study example of an extreme event with significant societal impacts is Tropical Cyclone Maria, which made landfall in Puerto Rico during September 2017. The tropical cyclone is one of the fastest intensifying storms in the Atlantic Basin on record. Just before Maria's center made landfall, with wind gusts over 160 kilometers per hour, extreme winds destroyed the weather radar in Puerto Rico. Rainfall from the storm was also extreme, with reports of more than 70 centimeters, which resulted in mudslides and severe flooding across the island. In terms of societal impacts, Maria is one of the most destructive tropical cyclones to hit Puerto Rico in the modern era. It's been estimated that the tropical cyclone resulted in close to 3,000 deaths, which included both direct and indirect fatalities, since it was nearly impossible to differentiate between the two types of fatalities for this event. Researchers generally ascribed a direct death as that related to hazards from physical forces of a tropical cyclone, such as flooding or flying debris. Indirect deaths generally refer to those that occur after a tropical cyclone, but as a result of tropical cyclone damage. Maria hit Puerto Rico in mid-September 2017, yet by the end of that year, nearly half of the island remained without power. So as you continue your studies and training on extremes and variability, I will leave you with this screenshot from the IPCC webpage, which is a salient reminder of societal threats from climate change. By empowering yourselves with the ability to analyze extremes in a changing climate, you are taking action.